All right, so let's have a look at these practice problems now. So in this case, we have a triangle JKL. We're going to let JK and JL have a length of 10 and KL have a length of 16. I want to determine the length of the three medians of this triangle here. Okay, so we're going to draw our three medians. And again, we're going to see how this works. So we draw up a median length. So let me call this here M. Again, remember that the median splits this into two congruent pieces, so there's 8 and 8. Now wait a minute. This here is an isosceles triangle here. So you may remember, wait a minute, if this is a median here, we know that the median to the base of an isosceles triangle is also an angle bisector, but it's also an altitude as well. And that's actually going to be really helpful. So there's going to be a bunch of right angles here. And then we can sketch the other two medians here. So I'm going to do this, and I'm going to do this. Now, you'll note that I'm using blue for each of these here. It shouldn't be too hard to show that these two segments here, let me call this here N and O. It shouldn't be too hard to show that LO and KN are exactly the same. Basically, you can, intuitively you can think of this as folding this triangle over JM here, and they should be the same here. So in fact, we're going to get JM, we're going to get KN, and that's it, because then OL is just KN. Now, JM, if you look at the triangle here, this is not too hard. It shouldn't be too hard here to show that in this case here, JM, right, in this situation here, JM squared plus KM squared equals KJ squared, right, because this is a right triangle on the left-hand side. So we have JM squared plus 8 squared equals 10 squared. Or if you know your Pythagorean triples, you know that JM, in this case, JM squared is going to be 36. That's 100 minus 64. So JM is 6. Okay, so that's one of the medians. Now, in order to get the other median, we're not exactly sure what to do about this, but we do know a couple things here. Let's look at our median. Let's look again what we have here. Let's call G the center here, the centroid. Now, in this situation here, we don't know what we have, but we can start filling in things. If we know JM is 6, one of the properties, again, we remember the properties of the median is that the centroid divides it into 2-to-1 ratio. Therefore, JG and GM are in a 2-to-1 ratio. If you split 6 in a 2-to-1 ratio, that's 4 and 2. So JG is 4 and GM is 2. And that's actually really nice here because you can see GM is 2. So now we have this triangle here. Let me yank that triangle out. Here's triangle LGM. Here's 8 and here's 2, and now we can figure out what GL is. So GL is just the square root of 8 squared plus 2 squared, which is the square root of 64 plus 4, which is radical 68 here. Now, if I'm not mistaken, that becomes 2 radical 17. But wait a minute. Again, note that G divides JM into a 2-to-1 ratio, so this is 2 radical 17. But it also divides all the other medians into a 2-to-1 ratio as well. So that means GL to GO here is 2-to-1. That's 2 radical 17, so therefore there's radical 17 at the end here. So therefore we now know that LO is 2 radical 17 plus radical 17 here, which is 3 radical 17, and that is also going to be KN here because, again, we've established the fact that all of these match with each other. So we have our medians here. Okay. All right, now let's look at this classic problem. Number 4 is a relatively well-known problem here. So we're told a couple of things about this. We have a parallelogram ABCD. M is the midpoint here of DC, and BM intersects diagonal AC at a point P. We're told that CP is 13. We want to determine the length of the entire thing AC. That's a weird problem. Well, I guess the only thing that we can do is start filling in what we know. We know that M is the midpoint here, right? So we know that this is going to be the case. So DM is equal to MC. Fine. Now, BD has been drawn in. I'm not exactly sure what that means, but maybe we can determine something. We know that the only other piece of information I haven't used yet is that ABCD is a parallelogram. Now, wait a minute. BD is a diagonal, AC is a diagonal. Let me call this point here over here E, their intersection. Now, one of the things you might remember about parallelograms is that the diagonals bisect each other, correct? Wait, the diagonals bisect each other. So that means here that AE and EC are the same. So that could be helpful. But it also means DE and EB are the same as well. So if we take a look at this here, BM, if we just ignore the top half here, just focus on triangle BDC, if we ignore ABD right now, M is the midpoint of DC, and we have a segment from B reaching down here. E is the midpoint of BD here, and we have a segment from C reaching there. Now we have two segments in triangle BDC that connect a vertex to the midpoint on the opposite side. Those seem a lot like medians. So BM is a median, and so is EC. And as a result, since these are both medians, P must be the centroid. So P is the centroid of triangle BDC. Now why is that useful? Well, let's see. Wait a minute. If that's the case, then the thing here, P is the centroid. We know the centroid divides every median into a 2-to-1 ratio. This is 13 here, so PEC to PE is a 2-to-1 ratio. If that's 13, then this is 13 over 2. So therefore we know EC here is going to be 13 plus 13 over 2, which is 26 over 2 plus 13 over 2, or 39 over 2. But wait, this is a diagonal of a parallelogram, and we know the diagonals of a parallelogram bisect each other. So therefore it makes sense that AC is just double EC here. So it's double 39 over 2, or 39. And note that it's no accident here, therefore, it's no accident AC is triple PC here. You can actually show, and we can just do this with other numbers here, right? Notice the only thing that happened here, the number was only useful at the very end. We can use this with any variable. So we can show that PC here is always 1/3 of the entire AC given a parallelogram like this.